Okay, so we've already gone through like test expectations. We did that, I don't know, 2 Mondays ago, last Monday maybe. So expectation on this one is I think there'll be a point where it's like, I don't get it. I don't get it. This is too much. DJ can't really expect me to do this. So I always like to show old tests and show that it really can come together. I don't know. I think the reason I do this is because it teaches you to put things into a story to see the big picture. And if you can understand each individual chapter, quote unquote chapter, and then get them all to stick together into a story, then it's actually pretty reasonable to memorize. And so these are just old tests, old student tests. And again, just showing you that don't give up before you've got it down, thinking that DJ's expectations are too high. It's a very doable test. You just got to get to the point where it clicks. It's definitely an A's and F's test. And as long as I'm talking about grades, I have to put in midterm today, but I don't really think midterm grades mean much early on because we still have more tests to take than what we've taken already. And so I'll put in an average of your score, but I generally don't even put in F's if I think like it's because you haven't taken a test or something. I generally will put in a D. So again, midterm grades are not that accurate because there's so many more points available out there. And part of the point of A&P1 is to get better at test taking. And so if you've bombed some tests, well, then let's just get better. All right, so we're going to draw this all out today. I'm going to flip down my Wacom so that I can draw. And we're going to try and get as much, I guess we don't have to get it done today. We can do it tomorrow. But it'd be nice to get as much done today so that you can switch over and start worrying about the bones and histology test. So I'm not really sure why I start backwards. I'm going to be following, this is the way I've done it, just always done it, is I figure that by the time we're done, this is the important stuff. So I guess that's why I start in the lower right, but you're welcome to do it in any order. There's 10 chapters here, 9 chapters. I call them chapters, but we're going to start at the very beginning. You're going to want to know action potentials pretty well because it's going to come back up when you do the heart in A&P2. And then I tell my students in A&P2 that sodium, potassium, and calcium are going to be so affected by things, everything from cardiac drugs in general, to a respiratory system, urinary system, and then also diet, drugs, respiratory system, and urinary system. And so we're going to take this kind of slow and break it down into really simple parts. But the first chapter of this story is what are the initial conditions? So my Wacom always starts to fine. So we're going to say, what are the initial conditions? And I always personify this a little bit, which we don't have to. What are the initial conditions? And who sets them up? That says, and who sets them up? And so you're going to draw a cell like this, especially if you take Henniger for A&P2, you're going to draw a cell like this 100 times. So this is just a pretend cell. And the initial conditions are set up by something called a sodium potassium ATPase. And so the sodium potassium ATPase is going to pump 3 sodium out. And I think we have time today. So if I start going too fast, I'll try and keep an eye on the camera to see if you're looking down or to see if you're looking up. 3 sodium out, and then I'm going to switch to purple. It's going to pump 2 potassium in. And I don't know that you really need to write this, but we could go way in and write it's going to burn 1 ATP. So it's like a revolving door. We learned about it in cells. Pumps 3 sodium out, 2 potassium in. So obviously, that's going to leave some space in the middle here. But we're going to write a bunch of sodiums out here. And again, you're going to write this right at the beginning of AMP2 when we talk about action potentials in the heart, all the way to the end when we talk about how the kidneys use the same very pump, the same sodium potassium pump to keep sodium inside of you. Now, there's going to be some sodium on the inside, so this pump isn't 100%. So put some sodiums on the inside. And of course, that's going to mean you're going to have a lot of potassium on the inside. Again, I'd rather take this too slow than too fast. So we're going to break it down into pretty small steps. And again, there's some potassium on the outside. So we're going to talk about the conditions two ways. One of the first conditions is you're going to set up, sorry, I wanted that back to black. You're going to set up, it's called a chemical gradient. Could be called a concentration gradient. And that means you're going to have sodium on outside of cell. And potassium on inside of cell. But also notice, and I'm kind of going to fib about this a little bit. I'll tell you the truth, but I'll also, we'll just go with the easier explanation is since you're pumping positives out of the cell, that means the outside of the cell is going to become positive. So you're pumping 3 positive charges out of the cell, but only 2 back in. That means you're like shoving positive charges out of the cell. And that means the inside has to be negative. That's always frustrated me that we talk about concentration of cells as outside relative to inside, but we talk about charge as the inside. So we could say the outside of the cell is positive, or we could say the inside of the cell is negative, and both of those are the same thing. But we talk about it as the voltage of the membrane, which we abbreviate VM, equals negative 70 MV, or millivolts. So every cell in your body has this charge. Most cells use it to get glucose in, so to let sodium come into the cell if it pulls glucose in too. But certain cells will actually use this electricity. It'll change this electricity quickly, so then you can move things like muscles or your heartbeat, and neurons do this too. So part 2, and again, it's one of those where there's multiple names, but there's also a voltage or charge gradient, and that is the inside of the cell is negative. Voltage of the membrane, again, I like to just be redundant. I know we already wrote this. Voltage of the membrane equals negative 70 millivolts. I said that that's a bit of a fib. So actually what happens, that accounts for about 15% of the charge, this whole like letting 3 sodium out and 2 back in. But the thing that really makes the voltage is there's leak channels in here, and potassium is able to leak out more than sodium is able to leak in. And when a potassium leaves the cell, that makes the inside of the cell negative. And that accounts for most of the negative 70 is these leak channels. But I don't know that we need to get that detailed. So this one's going to seem pretty simple, but again, I like to break things down really simply. Why do ions move? This one's going to be very close to the previous one. So one, there's a chemical gradient. And according to that chemical gradient, sodium wants to diffuse in. So there's a sodium gradient that drives sodium in. And potassium wants out. So that's the chemical gradient. That's the concentration gradient. But there's also a charge gradient or electrical gradient. So there's a charge or electrical gradient. And here, positive sodium wants in, how do I want to say this? Because inside of the cell is negative. So sodium is positive charge. The inside of the cell is negative. Opposites attract each other. But here's where it gets different. It's positive potassium wants to stay in the cell. Because the inside is positive. So there's this tension here where sodium wants in for two reasons, because it wants to get inside the cell because of the chemical gradients. It also wants to get in because of the electrical gradients. Potassium wants out because of the chemical gradient, but it wants to stay in because of the chemical gradient. It's going to be, I don't know if it's real important, but the chemical gradient is much stronger, much greater than the electrical gradient. It only happens once. It happens in muscle, where there's an ion channel that lets sodium and potassium flow at the same time. And in that case, it's called the nicotinic acetylcholine receptor. It's where a motor neuron tells a muscle to contract. That is a channel that lets sodium and potassium pass in each direction, and more sodium will come in than potassium leaves. But for the most part, ion channels, they only let one ion through. So then let's talk about, let me see where I am. Yeah, I got plenty of space, writing really small. Let's talk about, so leave a bunch of space below. Let's talk about how do ions move? I guess I probably wanted that in black. And here we're going to draw, maybe let me draw it first, because I have an eraser, but I imagine you don't. So we're going to draw openings. And we're going to do, first we're going to do, so this is, again, this is like a cell. And this first type of channel that we're going to draw is called ligand gated, or it can be called chemical gated. And the way we're going to indicate this is we're going to put like a little cup there. If it has nothing bound there, well, let's do this first. This guy's open and this guy's closed. So it's going to bind a little chemical and open this channel. And here's where I like drawing this out on a large sheet of paper, because you're going to see those types of channels over here. So here's what I tried to draw. And here is how they're going to show up. They're going to show up over there. Probably one of the hardest ones to understand, but it's really important, especially in the heart too, is you're going to have a channel. It's going to have a little gate, and that gate has positive charges on it. So if the inside of the cell is -70, then the gate stays closed. But if the inside of the cell gets a little bit more positive, let's say -55, then the channel is open. So it's got this little gate that slides up and down, has positive charges, and it responds to the voltage inside the cell. This one, there's 4 types of channels total. And I suppose we could have just made this one channel, because this is a leak channel. And it's always open. Small, but always open. And you won't get to that. You won't need to know that until the heart. The heart has leak channels. I mean, all cells have leak channels, but these have, in the heart, they're really important. And this one, just for the sake of having all the ion channels, even though this one, but the only place it really works is in hearing, and then also touch. These are called mechanogated. Sorry, these were called, up here were called voltage gated. And these down here are called mechano. Mechano is in force. And literally there will be a force. That's supposed to be a sound wave. The sound wave will tip the channel, will literally push the channel, and it'll make this one open. And here, if there's no force, then it'll stay closed. Okay, so what I'm trying to say is there's 4 main types of ion channels. The 2 last ones that we did don't come up very often. Leak channels will come up in the heart. Those are channels that are just small, but always open. Mechanogated, the 2 examples of those is a sound wave in your ear can open these channels, or also they're called mechanoreceptors in your skin too. So when you touch your skin, you literally push those gates open and the gates open up. Ligand gated will be kind of important today. That's when a chemical binds to a receptor and opens the channel. So that's when neurons talk to neurons. And then voltage gated is going to be really important all the way through the heart and through muscle, because they respond to the voltage inside the cell. The gate slides in and out based on the voltage inside the cell to open and close. Chapter 4 of our story is going to be pretty simple, but it's just like, let's not leave anything out. So what happens when ions move, let's go ahead and say move into or out of cells? And here we just want to be really clear that we get that sodium moving into cells will increase VM. Let's go ahead and define this now. This is called depolarization. Sometimes it's good to know that. So like a cell down here, it's polarized. The voltage is different on the inside than the outside. So polar means different. So this cell is polarized. Well, if we're going to raise this voltage from -70 up to 0, at 0, the charges are the same. And so it's no longer polar. It's been depolarized. And then again, just to be absolutely simple, potassium moving out of cells will decrease VM. And that's called repolarization. So I've always disliked this term, action potential. And I suppose down at voltage, I could have maybe write this word just so you know, trying to limit how many words, but maybe down here write potential. I want it in black. Another name for voltage is potential, like it's potential energy. Like a battery has potential energy. So sometimes we use the word potential. And so this is called, well, I guess first the question is, how does fast signaling occur? And the answer is action potentials. They're called action potentials. And again, I've never really liked that term. I guess it's because the voltage is changing. It's in action. And another name for voltage is potential. So an action potential is when voltage is changing. And so how we draw this is we say this is VM, so voltage of the membrane, and then this is time. And we don't really need to know what the time frame is, but it's on the order of milliseconds. So some key voltages typical in neurons is -70, -55, and +30 are really important voltages because a neuron will just sit, and if it's not doing anything, it'll just sit at rest. And then something will activate it to get it up to -55. It'll go up towards +30. It'll do what's called an overshoot. And then that's what the voltage will look like over time. Now what's happening here is this is called rest. This is called depolarization. This is called repolarization. And then this period down here is a time when the potassium channels stay open too long. So this is called hyper, as in you're going more polar, hyperpolarization. And then we're back to rest. When you draw this on yours, you can write this a number of ways, but I want you to be able to tell me what state the sodium channels are in. Probably could have done that in brown if I was sticking with my color coding. What state the sodium channels are in. And so when the channels are in rest, they are closed. Then I realized where I drew sodium channels is I draw them down here and I say there are voltage gated sodium channels and they open at -55 millivolts. So they will stay closed. They're voltage dependent channels. They'll stay closed unless you get to -55 millivolts. And the other channel we have to keep track of are, trying to erase a little bit, give myself some room. So the other channel we have to keep a track of for the action potential are, I guess I should write it up here, voltage gated potassium. And it opens at +30 millivolts. That's when it opens. And this is a voltage dependent. Sodium. Okay, so now you're going to want to take your time and get this because it's going to get more complex in the heart. It's obviously more important in the heart because we have a lot of drugs that affect the heart. Okay, so we're going along at -70. We haven't got to -55. We'll talk about how you get to -55, but when you get to -55, these channels are going to open. They're going to open until you get to the peak. I mean, we could also, if you see it on my diagram, I have sodium closed, and down here, potassium is closed. That was supposed to be purple. I want you to know, I want you to get this sequence. So I want you to know when each channel is open and closed. During depolarization, this guy is open. So drawing the little gateway up means the gate is open. And the potassium channel is closed. Now, sodium channels have a weird thing where they open very fast, but they also need to close very fast. And so they have what's called an inactivation gate. And so we're going to draw it like this. We're going to say the channel is technically open, but there's this ball that comes in and closes. So I'm going to draw it down here too. So this is inactive. Just really closes the potassium channels fast, having that little ball swing in. Now the potassiums are open. So if we go back and keep going with our bar graph down here, here the sodium channel is inactive. And then somewhere in here, it's hard to tell because whether it's inactive or whether it's closed seems the same. So the sodium channel goes through, I'm closed during rest, I open during depolarization, I turn inactive during repolarization, and somewhere in there, I change to closed. Potassium channel is going to be closed until right here. So it's closed. It's open and it stays open too long. That's why our voltage dips negative and then it's back closed. So seeing the sequence of closed, open, closed, or closed, open, inactive, closed, it's going to get more complex when you get to the heart. And so you do kind of want to get these, how these channels change this voltage. And again, the reason this happens is because some of the fastest way to move things is electricity. Now, this isn't the electricity that's in your walls, that's electrons. And that's much faster than these ions because electrons are way smaller than ions. But this is about the fastest the body can do something is using electricity with ions like sodium and calcium, potassium. Okay, so now I want to come back here and start to tell the story of, well, why do we care about all this stuff? So I'm going to draw a neuron, draw it in black. Obviously, it's not going to be the best drawing. So these out here are dendrites. This in here is the soma. This thing right here is going to be important. It's called the axon hillock. This is the axon. And then this is the synapse. We'll also want to draw on here myelin. So myelin in these neurons are created by oligodendrocytes. Now, I've kind of told the story already, but I'm going to tell it real quick. Is I got my PhD within the same month that Ella was born. This is my daughter Ella. And so I was supposed to go off and get like do research and stuff like that. But watching the people in my lab, people that work in science labs, I mean, they're working 60, 70, 80 hours a week. My boss would get in at 5 in the morning and he would leave at 6, Monday through Friday. So 11 hours a day. Is that right? 12 hours a day, 13 hours a day, 5 until 6. He'd stay 5 until 6 every day. So he'd stay 13 hours a day. And he'd still come in at 5 on Saturday and stay until noon. And boy, how many hours is that? That's a lot of hours. And so I kind of like just had this kid and had this cathartic moment and was like, I just can't work that much. I want to pay attention to my family. And so I talked my wife into letting me be a stay-at-home dad for the first 3 years, which was awesome. It was just amazing. Anyway, so I was never an umbrella kind of person. I didn't even own an umbrella since I was like 13. I mean, I remember my grandmother passing away and it was raining. And so I had to go buy an umbrella that day because the funeral was going to be outside. But anyway, I would never take an umbrella. But one day at 3, I was taking Ella to the gym. It was such a great time because it was like gym on Monday, library on Tuesday, play group on Wednesday. We just had our regular order. Anyway, I never took an umbrella, but we left the gym and it's rainy, and Ella has freaked out like twice in her life. She's normally a pretty calm person, but she just absolutely freaked out at the rain. Kind of like, I have a puppy. The puppy does not like the snow. Anyway, so I had to learn at that point, do I take an umbrella? And so I'm going to make this relatively brief. But so there's all kinds of things that might go into, do you take an umbrella? And so I'm going to break these down into pros and cons. And I'm going to make Ella like a huge, so this is going to be a synapse. That looks horrible. So that still looks horrible. I don't know what I'm trying to do here. There we go. So this is Ella. Ella, I had to learn right away that Ella was a big pro. And by pro, I mean, yeah, you got to take an umbrella. And then I remember, boy, when we had Ella, we only had like a Hello Kitty umbrella, literally the truth. And so I would never take a Hello Kitty umbrella anywhere because too tough for that. And so that would be a big con. Don't take an umbrella. Or maybe, I mean, it's kind of a weird year, and maybe you guys haven't experienced this yet, but usually in the fall, the parking lot is absolutely crammed shut. I mean, you have to park, if you get there past 10, you have to park way down in the other parking lot that's down near the tennis courts. And so that would be another, well, DJ showing up for an 11 o'clock class and it's raining out. He's going to have to walk a long way. So that's a pro. So what I'm trying to say is these are different factors that contribute to whether I take an umbrella or not. And it might be that I have too much to carry. So I'm just trying to think about things that go into this decision. And on yours, you're going to have to come up with your own decision-making process. A lot of times it's, do I go to class? Do I go to work today? Should I get a job? But you're going to come up with your own kind of decision-making process. I also like to throw in, like, what if my mother-in-law got really good at predicting really bad downpours, like it's really going to rain? And so right now, I'm not really going to listen to my mother-in-law. She's going to be way away from the axon hillock. And why we care about the axon hillock is the axon hillock, as I've said this before, it's if your neurons were guns, this would be the trigger. And the reason is because there's a whole bunch of voltage dependent sodium channels in here. So I'm hoping you're picking up the color coding and you're not colorblind. V-gated sodium channels. So literally what happens when you're trying to make a decision is all of these things. I mean, think about decision making. Think about, like, you have to weigh the pros and cons. And there's not only going to be pros and cons, but there's going to be different strengths of pros and cons. Like Ella is very strong. For the next 5 years, if I was taking Ella anywhere and it was raining, I'd never forgot an umbrella because that event was so strong. And so this one's going to be a very huge pro. And it's enough on its own. I should have actually wrote pro like really big. It's enough on its own. It was enough on its own to say, yeah, I'm taking an umbrella. Whereas, you know, if L is not with me, maybe other things have to factor together. So there's a certain math that has to happen when you're making the decision. Again, you've got pros and cons, and each of those are different strengths. And so the way this is going to work, just to jump ahead, is the pros are going to let sodium in because that will depolarize the neuron. And the cons, again, jumping ahead, they're going to do two things. They're either going to let potassium out or they're going to let chloride in. So you see there's this math of these ions where the sodiums are trying to raise the voltage. So this has to get to negative, I'm going to put it in brown. The axon hillock has to get to negative 55 millivolts. Because if it gets to negative 55 millivolts, it activates all of these sodium channels, and that's going to depolarize the neuron. And then ion channels just kind of have a timer to them, like they just close at a certain time. So if the pros win, if I get more sodium down here to raise 55 versus potassium and chloride, which are trying to take me further away from 55, trying to make me more negative, then I will actually trigger the action potential. The sodium channels will open. I will depolarize. That channel will inactivate. Potassium channels will open, bring my voltage back down, and I've gone through an action potential. And technically what's happening in an action potential is in these little gaps, there are sodium channels. There are also potassium channels. Now this is always really hard for me to teach. And there's no great animations. But you just have to take your time and realize, okay, I'm going to weigh my pros and cons. And if I get to negative 55, a whole bunch of sodium is going to pour in. And when that sodium pours in, it's going to raise my voltage. And then the sodium is going to flow down the axon. And the myelin is going to prevent it from leaking out. And so now I'm going to get this down here to negative 55. If I get that to negative 55, then sodium's going to come in. It's going to go down to the next node. And that's going to get me to negative 55. Sodium's going to come in. Sodium's going to come in. And this is called saltatory. Salt in Latin means jump. Saltatory conduction. So as we go down the neuron, we're going to take ourselves up the action potential. And then if sodium is coming in this node, then potassium is going out in this node. So we're going to bring our action potential back down. Or as sodium is coming in over here, then potassium is leaving over here. And so that's going to bring us down our action potential. And so what's going to happen is the sodium is going to jump out, potassium is going to come in, and this signal is going to jump down the action potential. So this is called jump down the axon. So this is called an action potential. And eventually what you're going to try and do is you're going to get this down here to plus 30 millivolts. And we'll see why that is in a second. But the other thing I want to point out is it's probably good to know that there's two different types of potential. These out here are called graded potentials. And a graded potential simply means, I want to leave some space over here. A graded potential means, leave a gap, means that the ions come in like sodium comes in, and it just spreads around. So up in here, sodium comes in, potassium leaves, chloride comes in, and it just kind of all mixes up. There's no voltage gated channel to pump things back up. Whereas here, the action potential out here, you're gonna have to just draw over it. You're gonna have a bunch of voltage gated channels. so that when the current comes in here, it comes over to here and activates the next set of channels. Comes in here, moves over here and activates the next set of channels. And so this is an action potential. Whereas over here is called a graded potential. So this happens in dendrites, and this happens in axons. Okay, so that's probably going to take a little time to get that one to settle in. But I do think it's pretty cool to get that, yeah, I've got a lot of things that go into whether I make a decision this way or that way. There's pros and there's cons, and of course there's different strengths. Right now, we haven't written about the different strengths. We've just said, hey, there's pros that make me want to take an umbrella. They're going to fight against the cons. If the pros get enough sodium to come in to overcome the potassium that's leaving and the chloride that's coming in, then I'll activate the action potential by activating the axon hillock. And then sodium will run down the axon and keep the signal going. And eventually then what would happen if this was really your brain? You would start to you'd either take a note or you'd think about where your umbrella is. You would say, okay, I'm going to take the umbrella. Now I got to think about, hey, make a note of that, or hey, don't forget, or hey, where is your umbrella? In our house, it's pretty easy because we have like an umbrella can right at the front door. Okay, so that's pros and cons, but I also want you to get strength, and I also want you to get learning. So chapter 6, if you can squeeze it in down here, how do you get various strengths of input? How is Ella very strong? That's enough to say, yes, take an umbrella. But it might take 3 or 4 other positive things. I could have added more things to this, like maybe I'm carrying my computer and I don't want it to get wet. Or like this tablet that I'm drawing on doesn't have a very good case. And so if I was taking this into campus and it was raining, it's supposed to rain and snow all week. So if I'm carrying this into campus, then yeah, I'll take an umbrella. The first one is, we could call this Ohm's law. I want you to start to get Ohm's law because Ohm's law also comes up in respiratory. Ohm's law is basically how something flows is determined by how much it wants to flow versus resistance. And so our first thing here is the closer the synapse is to the axon hillock, the stronger the input. So I specifically put Ella very close to the axon hillock. So again, what Ella's going to do as a pro is she's going to let sodium come in. And since this sodium is right close to the axon hillock, this is going to be a way stronger input than mother-in-law. Because this sodium has to travel all the way down here in a concentration sufficient enough to stimulate the axon hillock, whereas Ella is really close. And so a synapse that's close to the axon hillock will be stronger. Another one, and this probably makes sense. I guess I didn't really draw my dendrites different. The wider the dendrite, the stronger the input. So again, we're thinking about moving ions of sodium towards the axon hillock. So it's kind of like trying to move a bunch of people down a hall. If the hall is wider, you can move more people. So let's say this dendrite over here, let's put something over here on this really narrow dendrite. That's going to be a weak input. Like let's say hair looks good. That's not going to be a strong input for me. So it would be on a dendrite that's really narrow, and then it's going to be hard for this to get enough sodium to come in and make it down here. So that would make that a weaker synapse. And then the last one is simply how much neurotransmitter can you release? So we haven't talked about this yet, but these synapses are going to release neurotransmitter. And that neurotransmitter can be a pro or it can be a con. More neurotransmitter equals more signal. Yeah, let's just leave it at that, more signal. We definitely know that we're really sure. We know B and C can change in learning, and probably A. So let's say my mother-in-law develops this uncanny ability to tell me, hey, it's going to rain a lot today, it's going to rain bad. Like, I'm not really picking on my mother-in-law, I get along with it, but it just seems like someone to pick on. So this mother-in-law, technically we've learned that it can make this bigger. So dendrites can change in size with learning. So one thing that can happen is this can get bigger. That's learning. It's also thought that it can move closer to axon hillock. Your synapses can rearrange themselves, and that's learning. And also, it's pretty clear that we can make more neurotransmitter. So these not only give you different strengths of input, but it also explains how you learn, how you change your relationships. Like I had to definitely change my relationship with umbrellas when I had Ella with me. Okay, so we kind of already said this, but we might as well come back and say it. I never know which order to go in here, but chapter 7 is how do you get pros and cons? And pros, quite simply, let sodium into dendrite. And then cons, those are going to be chemically gated channels that either let potassium out, so that would make the voltage more negative and further away from 55, or let chloride in. Now, we could go down here and do that just to make it clear. The chloride is on the outside. It's pumped to the outside. And we could write up here too. When chloride moves in, it decreases. Yeah. Almost there. 2 more chapters. I think if we get this drawn today, then we probably just won't even meet tomorrow because, well, I mean, I'll be on here, but I won't do any new content because that'll give you that solid 2 days to study for the practical. Taking a little mental break. So we have chapter 8 and chapter 9. Chapter 8 is about 5 steps long, but I like to pretend I'm focusing down here somewhere. And so I'm going to draw. Well, first let's label it. We're going to do synaptic transmission. And so we'll do one synapse. It's going to be a pro. And one synapse. It's going to be a con. And then this down here will be the umbrella neuron. And so the first thing that has to happen for both of these, doesn't matter which one we do, is one, we have to get to plus 30 millivolts. So this has to get to plus 30. We also drew it, that's why I wrote this down here, plus 30 millivolts. What happens at plus 30 millivolts is there are, so this is going to be step 2, V-gated calcium channels. So this is going to let calcium come in. So these are just like the other channels, except these are calcium. And sitting in this membrane are going to be a bunch of chemical gated channels. And in the case of pros, they're going to be sodium channels. In case of cons, they're either going to be, they're going to let chloride in, or they're going to let potassium out. So the way this works is there's these little vesicles. So there's little vesicles, so little sacs of membrane, and they're stuffed full of neurotransmitter. So they're sitting there and they are attached to the membrane, but they're not open yet. So these are called synaptic vesicles. Interesting side note is botulism toxin works by cutting these vesicles loose. So then the neuron is activated, but it won't release neurotransmitter. And it takes months for those vesicles to get themselves set back up and attached. So that's why when you inject Botox in your forehead, it'll paralyze those muscles for several months, but eventually you'll get those synaptic vesicles back. Or it's also why Botox can be so lethal, because if the Botox gets to your respiratory system, then you won't be able to breathe. Okay, so I'm gonna write it down here. Get to wherever you can get it. You're gonna write get to plus 30, get synapse to plus 30. V-gated voltage dependent calcium channels open. Calcium opens synaptic vesicles. And that causes neurotransmitter to be released. NT is neurotransmitter is released. So I try to do it here. I'll try and do it up here too. Step 3 is calcium opens vesicles. And then step 4 would be neurotransmitter is released. And so when that neurotransmitter is released, it'll bind to the postsynaptic receptor. We should probably put those terms in too. So this whole thing is called the synapse. That makes this the presynaptic receptor, presynaptic neuron. And then this is the postsynaptic neuron. So before the synapse and after the synapse. There's two more terms that you should know here. One is called, this is called an EPSP. Pros are called an EPSP. That stands for excitatory postsynaptic potential. So it's going to excite the postsynaptic neuron by changing its potential or voltage. And then this is called an IPSP, which stands for an inhibitory. And you'll see if you're going to do neurotransmitters, neurotransmitters are here, and you'll see that some of them have a negative sign. Like GABA and glycine, and this is N-methyl D-aspartate, and this is glutamate. So glutamate is a pretty typical positive neurotransmitter, causes EPSPs, whereas GABA, glycine are pretty negative. They generally open chloride channels or potassium channels, so they're negative neurotransmitters. This is one of those interesting ones where a little bit of truth is probably true. So if you've heard of MSG, monosodium glutamate, some people think that monosodium glutamate leads to seizures or overexcitability because you're actually eating the neurotransmitter glutamate. But then again, it is just an it is just an amino acid, which we're eating amino acids all day. All right, the last little thing that we have to do is how do you clear extra neurotransmitter? Sorry, I wanted to come up here. Try and squeeze it in right here. The chapter 9 is clearing neurotransmitter. And so I'm going to pick positive this time. So if this, again, trying to squeeze this in, if this is a big synapse, and this is the postsynaptic synapse, we want to, the rule is you should release enough neurotransmitter, NT, to stimulate each receptor once and only once. So you should release enough neurotransmitter that you hit each receptor once, but while that channel is open and before it closes again, you get rid of all the extra neurotransmitter. Let me say that again. You release enough neurotransmitter to hit each one of those receptors, but before they have a chance to close, you get rid of all the other neurotransmitter that's left over so that you can't stimulate the receptor twice. And the way you do this is, one, you have reuptake pumps. And so these are going to be pumps that, I don't know how I want to draw this, but you'll have pumps that pump the neurotransmitter back up in the vesicles. And the reason you want to know these is there's something called SSRIs, selective serotonin reuptake. You don't need to know this name, but you probably heard of SSRIs because they're antidepressants. And at one point in this country, 1 in 3 of us were on antidepressants. And so what SSRIs do is they inhibit those pumps and it leaves serotonin in the cleft, and that seems to help with mood. The second thing you can do is enzymatic breakdown. So in some clefts, synaptic clefts, you have these little enzymes that will grab the extra neurotransmitter and break it apart. And that's pretty common. That's the main example of that is in motor neurons. Motor neurons, the cleft is cleared by enzymes. One reason to know that is sometimes if this receptor, so like if this is a motor neuron and this is muscle, sometimes you'll develop an autoimmunity to those receptors. It's called myasthenia gravis. And so the immune system will start attacking those receptors. And one of the ways you can counter that is to inhibit the enzymes. So then the neurotransmitter sticks around longer. And the last thing is simply diffusion. So sometimes this neurotransmitter in here will just diffuse away. Will just get out of the cleft. And then it's usually cleaned up by things like astrocytes. All right, so trying to find my rubric. So I think you have access to this. This is going to pop up, might be laggy. But so you're going to be asked to draw out this drawing. And I think you have access to this. It's probably on the practice test. But let's just go through it quick and against my drawing. If I can get it to snap to the side. Okay, so I have my sodium, potassium, ATPase down here. I have the sodiums on the outside. I have the potassiums on the inside. I have the chlorides on the outside. I've written that the VM is -70. I have my 4 types of ion channels. So I have weak, voltage-gated, ligand-gated, mechanogated. I have, well, I might have skipped a few, but you're going to have 7 factors in the decision. So 7 pros and cons of, do I study? Do I go to class? Do I become a nurse? Do I become a rad tech? What do I, you come up with your own decision. Do I have your axon hillock labeled? Do you have graded potentials labeled and action potentials labeled? Do you have myelin? Do you have Ohm's law? So the 3 factors in Ohm's law: the size of the dendrite, the closeness of the dendrite to the axon hillock, and the amount of neurotransmitter. Do you have the action potential drawn correctly? So don't just, so sometimes people get haphazard and they'll just draw like this. I mean, there's a very specific shape. If I could get my Wacom to work. There's a very specific shape, and I want you to have that shape. So do you have it drawn correctly? Do you have when the sodium channel is closed, open, and active? Do you have when the potassium channel is open, closed? And make sure, because I've seen some people not have these lines lined up. Like, there's a very specific reason why this line is right here. It's because it's lining up at the top with this line right here. So make sure those are lined up. Do you have rest, dipole, repole, hyperpolarized, and rest drawn? For synaptic transmission, do you have the +30? The +30 can be here or it can be up here. Do you have an IPSP and EPSP? Do you have the sequence is that you get to +30, you open the voltage-gated calcium channel, calcium enters, calcium causes the vesicle to open, and neurotransmitter is released. Then do you have, the way that you clear is you should have release enough neurotransmitter to activate each channel once and only once, and then you clear the rest with diffusion, reuptake, and enzymatic breakdown. So that ends up being 76 points. If you want to add, like, I think it's not enough. It's not important enough that I really want to make you get neurotransmitters, but if you want to make, I think, is this the test where there's only a few? No, I guess there's, I don't know, 15 multiple choice. There's not a lot of multiple choice. So if you want to memorize your neurotransmitters, you can. I mean, there's some value, like things like this come up later, like these novel neurotransmitters that are really fast. Nicotinic acetylcholine receptor and muscarinic comes up later. So direct ion channels are kind of like what we were drawing over here, where the chemical binds right to it. Indirect are you go into the cell and you change channels from inside the cell. I mean, like substance P, that's why after you hurt yourself, that whole area becomes a little bit more sensitive to pain. Endorphins are cool. So those are worth 5 points of extra credit if you want to do those. I'd have to go back and look at test format, but I think there's a few questions about skin and neurons, but not that much. Let me see what's trying to look up test format because I guess it's slipping my mind right now. 14 multiple choice. There's this essay on cancer of the cells of the brain, and then the umbrella metaphor is 76. So yeah, that adds up to 76, 86, and then 14 multiple choice, so the test will be out of 100. But obviously the main thing is to be able to draw the umbrella metaphor. Any questions?